Hello, everyone. This is Sri Krishna from Deso Systems. Welcome back to those who joined our very first session last month. If you're new, this series is called SolidWorks Cloud Simulation Champions. And today we have a very exciting and unique session on designing antenna systems that are compliance ready and that get integrated into wireless applications across different industrial scenarios or industrial technologies. And I am joined by my friend and awesome antenna engineer and a senior hardware engineer from Inovonics, Mark Zackham. Hi, Mark. Thanks for joining us.
Hello, thank you for having me. I'm excited to talk about this.
All right, thanks, Mark. For those of you who are new to this series, this is for our SolidWorks customer base. If you're a company that's using SolidWorks in your design and innovation process, this is for you to learn about how you can accelerate your product innovation, reduce cost, time, and effort, and build better products, bigger portfolio in shorter amount of time, leveraging the power of cloud-based 3D Experience Works portfolio, especially with the integrated modeling with SolidWorks and simulation from the Simulia-based technology that's being offered on 3D Experience platform. That said, this session is going to be recorded. So in case you miss or in case you're not able to go through the entire session, you can always come back to our website and watch the session. Okay, without further ado, let's go ahead and get started. Mark, why don't you share a little bit of your background with our audience and then we will dive right into it.
Yeah, of course. I'm Mark Zackham. I'm a staff hardware design and regulatory engineer at Inovonics. For the past 3 years, I've been in charge of all our new antenna designs for our past and present products when it comes to either revamping an old design or creating something custom from scratch. And we account for almost every single scenario where our devices would be set up in. So I've had, thankfully, a lot of experience making antennas for various different scenarios.
All right, and this is a very unique domain or unique background to have because a majority of the SolidWorks users that we talk to are typically from either mechanical or electrical background or manufacturing background. So it's really nice to have you on the call, Mark. Okay, with that said, let's go ahead and get started. Maybe tell us a little bit about Inovonics to start with.
Yes, of course. Inovonics is an industry lead in wireless technology. We are in the fields of security, senior living, and the whole range in between. We're in commercial markets. Most of our products can be connected to the cloud and have on premise application abilities. We have flexible and cost-effective solutions, and all our stuff is purpose-built. When it comes to our software, our APIs, even our hardware, everything is custom. We build it for that purpose, and that's what we're known for. We're known for custom solutions that work every single time.
All right, and tell us about the applications that you guys typically offer.
Yeah, so our main markets are senior living. Senior living is huge, as well as commercial security. And then the other markets that we're also in are multi-family submetering, as well as commercial monitoring.
For a layman like myself, what does submetering mean in very simple terms?
Submetering, as let's say you have an apartment complex and you want to see the water flow through the whole building and manage it.
Mhm.
We have our wireless technology that can basically manage it per household. You know how much water is
Okay.
coming in. Also leak detection. So if you're seeing abnormal flow, we can detect that, and that could trigger a system to then cut the water flow. That's within that industry.
Very cool. Yeah, exciting stuff. And for our audience, if you have any questions while we are having the discussion, feel free to type in your question in the Q&A section in Zoom. We will try to take them up at the end. If not, we will reach out to you and try to get a response as early as possible. Okay. Before we dive into the exciting world of antenna design, maybe we should take a step back. And Mark, maybe you could explain to our mechanical design centric audience the importance of electromagnetics and how that ties to the antenna design process.
Yeah, so everything involved in our lives involves electromagnetics. Everything. Our light switches, your phone, any call you make, the Wi-Fi, wherever you go, you are going to be surrounded by electromagnetics, electromagnetic interference, devices around you. Whether we like it or not, they're always there. But that is not a bad thing. We design things in the industry to make sure that all products that are approved in the market are not only safe for people, but safe for the environment around them. And things that are higher powered that might be unsafe always have the safeguards to make sure that people in that area are well accounted for.
All right. And when we talk about electromagnetics, it's such a big field with so many different applications. Maybe you can break that down for us.
Yeah, so in the world of electromagnetics, we have everything from static, so just the lowest of the frequencies that you can think of, all the way into light, basically the fastest that we can think of. And in between that spectrum, it covers everything that we do on this earth. Everything from sensors, our transformers, our generators for power, our electric cars, motors, the antennas that I design, larger antennas such as the 5G networks, 4G that we have online. We have the security systems at the airports to x-ray you and make sure that you got that everyone is safe in the airport. And then we have photonics. We have high speed design. We can cover the entire spectrum when it comes to high speed or low speed when it comes to electromagnetics. And that's the beauty of it. It's involved with every part of our lives.
So, is it fair to say that electromagnetic simulations can help companies design, not only design these products, but assess their performance even before they are prototyped, and help get to market, quickly while ensuring that the compliance needs are met?
Not only do I think it helps, I think it's a necessity. I think
Mm.
this day and age, with how complex designs are and how custom built things need to be made, without simulation, you're wasting time. And in the industry, if you waste time, you're wasting money. Um, are these simulation tools that we have access to through 3D experience not only help us make the design process quicker, but more accurate and safer for everyone. We can account for our compliance issues before we ever even build the product, which means we have less time redesigning, less time worrying about sending it to the lab, waiting for it to come back, and more time just working on getting a working, functional product out to the customer.
Right, that's a very good point, and I guess we're gonna dive deeper into this in the context of RF antennas in today's conversation. Right. So, can you, before we dive straight into it, can you give us some examples of each segment or each, frequency of applications in electromagnetics?
Yes, of course. I think before I begin this, it's important to understand what it means to be low frequency, high frequency, and so on. Every frequency has a wavelength. The lower the frequency is, the longer the wavelength is. And the difference between the length of the wavelength and the size of the actual unit displaying that frequency is what determines whether it's low frequency or high frequency.
Oh,
If,
okay.
yes. So if you have something running in the hertz or like not even kilohertz, just 100 hertz, 10 hertz, its wavelength is going to be extremely long.
Right.
Basically, it's going to be so long that it's not a radiating subject. And that's what
Mhm.
we determine as low frequency electromagnetics. Once you get into the higher frequencies, kilohertz, megahertz, gigahertz, so on, its wavelength is a lot shorter compared to the size of the device, and that actually creates a radiating field. And that's where we can consider those as high frequency electromagnetic applications.
Wow,
And then,
that's interesting. So it's not just the frequency or wavelength of electromagnetic waves, but it's also the size of the device that determines whether it's a low frequency or a high
yes,
frequency
and those
application.
two basically directly correlate with each other. There's
Okay,
never one without the other.
got it. Okay.
as in the smaller the lower the frequency, the larger the antenna or radiating source. The
Right.
higher the frequency, the smaller the radiating source or the smaller the antenna.
Right. So the antennas fall under the class of high frequency applications because typically the devices are relatively small, but the frequencies pretty high.
Yes, and they're considered as radiating units, and that's what
Mm.
we consider as antennas.
Okay. Wow. I learned something new today. Okay. So let's talk about antennas then. We see antennas everywhere. And
Yes,
yeah, go ahead.
yeah, we see antennas basically wherever you go, even if they don't even look like antennas, they're everywhere. They're hidden, they're not hidden, they're in your phones, they're in places you wouldn't expect. We have come a long way from 100 years ago to now of how we can send out wireless communication, how we can talk to each other. And it's pretty incredible where we have these scenarios set up and how effective we've got them to be.
Right. Yeah, yeah. And it's no longer just limited to one or two industries, right? In the past, you would assume antenna would be related to telecommunication industry or the high tech manufacturers. Now we see antennas everywhere, as you pointed out.
They're everywhere. They're even in cat toys. They're everywhere. There's not a thing that you can find. If it's connected to something, your phone, Wi-Fi, it has antennas in it.
In fact, it's interesting you bring this up. Yesterday, I met a gentleman during my train ride. We just started talking about the different technologies that our companies develop, and he mentioned that he works for a company that builds GPS antennas that go into agricultural equipment,
Wow.
and basically the company that owns multiple equipments and offers it as a service is able to track the location and then other antennas to track the performance of their agricultural equipment. I thought that was cool.
That's incredible. Yeah, the benefits are endless. Just that as an example, making sure that farmers know where all their equipment is, they can
Right,
see performance, they can understand scheduling, just all from being able to connect to the field and what they have in their environment.
right. Yeah. So tell us a little bit more about how the antennas work, how they operate, and what are the key considerations in the design process.
Yes, of course. A little focus on high frequency here. Closer example of where we have these antennas. Your car, if you notice, has a little blade on top. Almost every single car has this blade on top. That is
Yes.
how it communicates with everything. Most cars have Wi-Fi now too, but
Mm.
they also need a radio antenna. How are you going to get your AM and FM signals to come through? We have Sirius XM, which is another different antenna band as well. And now we have your phone. Your phone has just a plethora of antennas. Now with 5G, 4G, and 3G and 2G, we have every phone has to support all those different bands depending
Mm.
on the scenarios that it's in. Wi-Fi and Bluetooth and GPS. There's maybe I would say over 10 different types of antennas that are in every single phone on the market, and this is a necessity. And the beauty of it is we can design those systems nowadays because we have tools like this to make sure that these different antenna systems in such a small device don't couple with each other, don't interfere with each other, and don't degrade the performance when it's most needed. So these are just some of the examples that we can see.
Yeah, and that's interesting because a lot of our SolidWorks customers, I would say around 50-60% of our SolidWorks customers, they don't design antennas. They would buy it from, a third party or a supplier. Would it be fair to say that they could still benefit from leveraging electromagnetic simulation in order to find the best location of the antenna, and also in order to assess the integrated performance? Because I would assume that when it comes to compliance, it's the integrated performance that matters and not the standalone performance.
Yes, so that's a really important factor. Not everything is custom. A lot of antennas and most manufacturers use off-the-shelf components. These are
Mm.
ceramic chip antennas that have already been designed, and the benefit of those is they're extremely small, extremely compact, and can be placed in devices like phones and laptops. It's really important that you have a software that's capable of simulating these off-the-shelf components, and that is exactly what we can do specifically within CSD Studio, because you can get the design files, you can get the output files needed for all these different ceramic chips, and you can simulate the results. And then, now that you have them all placed within your device, you can see how they all affect each other. And it's important from the SolidWorks aspect that we have an enclosure that is as close to life as possible, so that when all the components are placed down in their respective locations and we run our tests, we know exactly how the performance is going to be, the materials it's interacting with, and what it's going to look mostly for how it's going to be in the real world.
Very cool. And what are the typical questions that we try to answer? For example, here we have two arrays of antennas that are next to each other.
Yeah, so placement of antennas in almost any environment is extremely important. Specifically, when you're talking about outdoor, the example we're looking at on the screen right now is for 5G.
Mhm,
5G is really high powered, and that means it's pretty directional too. It doesn't
mhm,
have as wide of a span as 4G and 3G because 4G and 3G are at lower frequencies. So having an antenna array that's accurate to basically for the desired area it's supposed to radiate in to work and not couple with each other or couple with the structure that it's within
mhm,
is really important to know and set up within these softwares. When it comes to indoor use, we're less worried about exact direction location because indoors we have multipathing. Basically, that just means that the waves bounce around everywhere.
mhm.
Eventually, it's going to meet your device. But when it comes to outdoor applications, it's extremely important to get these arrays correct, their location set, their angles, offset. All of these are really important.
Eh,
We'll know. Oh, sorry. Yes.
Yeah, I was just going to ask, and how much is the enclosure or the casing going to impact the performance of these antennas from a mechanical
Depending
standpoint?
Oh, yes. The enclosure is the most important part for any antenna structure,
Mhm.
specifically depending on the materials it's built on too. If the correct materials aren't chosen, then we could have serious issues. Like metal is the antenna's worst enemy. You don't want to
Okay.
cover your antenna in a metal box. It's just not going to work, or a
Mm,
Faraday cage, or whatever it is. So
mm,
designing an enclosure that accounts for the antenna's radiation to make sure it doesn't inhibit it in any way is extremely important. And that's where the mesh between the mechanical engineers, the SolidWorks engineers, and the simulators come into place because it is true teamwork at that point. Um, and that's where the back and forth comes. A SolidWorks engineer could design an enclosure, send it to the simulation engineer. He'll run his test and be like, "Hey, we're having some issues. Could we maybe drop this wall by a couple inches or a couple millimeters, depending on the situation?" Or, "Hey, this material is really not working for us. We're going to need to find another material. Can you uh, set up the structure with this one instead?" And so on. It's really important to get the enclosure right because that is what the antenna will be directly interacting with from its get-go. In outdoor applications, it's the enclosure and then just the air. So it's really
right.
important to make sure that that is what we have set up correctly.
Yeah, and also the other scenario could be the SolidWorks user could be the user of the electromagnetic simulation themselves, right? Where
Oh,
they're just
yes.
assessing the right location and the material choices and so on.
So if set up correctly within the 3D space, the 3D experience space, it can just happen that the simulation engineer has all the parameters already preset
Mm,
and basically communicates to the SolidWorks engineer saying, "Hey, you mess with this parameter, you'll change the angle of the arrays. You mess
mm,
with this parameter, you'll change the separation, whatever it needs to be." And
right.
then basically the SolidWorks engineer knows like, "Okay, sweet. I can mess with the enclosure as much as I want and I'll rerun it." And either they have a good understanding if it's going to affect performance or not, or they can share with the simulation engineer like, "Hey, I moved the array to a 60-degree angle instead of a 55-degree
Mm,
angle. These are my
mm,
new results. Do these look good?" Go
right.
from there.
Okay, yeah, very interesting. So I like how you mentioned that metal is the worst enemy for electromagnetics. Is there a particular type of material that's preferred when you have antennas in place? How about
Plastic.
plastics? Okay, there you go.
Plastic, wood, drywall, all these are non-interfering. Some have a little more effect than others. It's also proximity and thickness of these materials are really important too.
Right.
So I can tell you plastic, but if you have a foot thick plastic and it's directly on the antenna, it's going
Of
to be a
course.
way different performance than half an inch thick plastic a couple
Right.
millimeters away from the antenna instead. So
Right.
it's all perspective, but the least interfering material would be plastics, woods, that sort of stuff.
Okay.
Um, yeah.
Yeah, that's very interesting to know. Also, tell us about the scenario where the antennas could actually be competing with each other.
Yeah, so in the electromagnetic world, there's something called coupling, interference. There's also something known as harmonics. So
Mhm,
everything that radiates at one frequency will radiate at double, triple, quadruple its frequency, so on.
mhm,
In most antenna designs, that's accounted for within it. Or there's clever filtration systems to make sure that whatever is being received is just the main signal and not the harmonics afterwards. But it's also really important to understand the physics of the physical layout
mm,
of separation between these antennas, making sure there's enough distance, making sure that the orientation of the far field radiation is correct, so you don't have anything
mhm,
pointing at each other or too close within their near field, because that's where you'll get a lot of these issues. And also, talking about placement, if you've noticed, most phones are today are metal and glass, and you're like,
mm,
well, how are they going to communicate anything? How are they going to get anything out? Didn't we say that that's our worst enemy? Well, if you look
mhm,
closely on most phones, you'll see different bands on the bottom and top and on the side. Those are made of a completely different material than the metal and glass to make sure that the antenna signal can get out of there perfectly. Sometimes it's the antenna just under a piece of plastic, and what you're feeling is actual plastic on those
mm,
bands, and
mm.
that's how the antenna can actually radiate from these metal and glass phones.
Wow, very cool. So, in a sense, there could be a scenario where the multiple antennas can actually be cooperating with each other instead of competing with them.
Yes, there. It goes both ways. You
Mhm.
can design multiple antennas to avoid each other and make sure performance is good,
Okay. Yeah.
or you can have multiple antennas to then boost whatever you're trying to make. You can have
Okay.
multiple arrays, let's say for 5G. Since 5G is so finicky and so localized, you would like to have multiple arrays of 5G to maybe account for
Mm,
a different spectrum of uh, how it wants to transmit and receive its signals. So maybe
okay.
having 3 arrays of 5G within the phone, it just makes it so it can account for more.
Mm. Would that also help in redundancy? For example, if one of the antenna fails, the other kind of picks up the transmission
Yes.
requirements.
So basically, in the redundancy sense, is if this antenna located here and this antenna located here, both for the same purpose,
Mm,
if your signal is coming from a different source, you're going to have a higher you're gonna have a higher chance of the antenna on the left to catch what the antenna on the right couldn't, as a very
okay.
simple general view of
Okay.
looking at it.
Okay. All right. Yeah. Very interesting. Let's switch gears a little bit. Talk about compliance. I mean,
Oh
it's
yes.
important to understand, the electromagnetics. We talked about the whole band and the fact that antennas fall under the high frequency category. We talked a little bit about antennas, but it's very important to make sure you design antennas which can actually go to market, and that's where compliance comes into picture. So tell us a little bit about the importance of certification.
Yes, the favorite part about my job. No, that aside, compliance, if you can't make something that falls under the compliance rules of whatever country you're in, so specifically, let's think about FCC and Canada's FCC, I said, um, if your product does not comply under their standards, you cannot sell it. You cannot have it in the public. And if you do, you'll get a crazy fine. And probably jail time. You don't want to do it. Designing within these parameters is tough, and you need to design for them from day one. You can't just make an antenna and then, all right, we'll change it to comply later. You want to have that in mind from day one when you're starting to design something, especially if this is a device that gets near the human body. like a phone near the face, a watch, a pendant, anything that has contact with human or close proximity with human. You want to make sure that either you're SAR certified or your device is low enough power to get exempt from it. When you're working with high frequency, like really, really high frequency applications, such as the 5G gigahertz, the 5G network towers,
Mhm.
people should not be anywhere near that. They're
Mm.
really high powered. They're dangerous.
Wow.
That means when you go through its testing and certification, it basically gets you into a certain situation where you're like, okay, we've certified this. People need to be within 100 meters of this antenna. That's their
Mm.
safety range. And then you'll have the necessary warning signs, and you need professional personnel to get in within those fields. You need to turn off those systems to do maintenance, stuff like that. So we
Mhm.
have compliance on every level from the lowest power to the highest power systems to make sure that whatever it's coming in contact with, they're either aware of the situation or it's
Mhm.
already intrinsically safe for the person.
Right. Yeah, yeah, that's interesting. And earlier you mentioned something about compliance with respect to other devices. So, is it fair to say that there are two high-level categories of compliance that a manufacturer has to pass?
It depends on your product.
Okay.
So there's different levels of compliance depending on what you're making.
Mm.
If you're designing a phone or if you're designing like a high-powered like antenna array, those are two different compliance sections. If you're
Mhm.
designing a low-powered unit that gets near the body, or you're designing a device like a mouse that you only have in your hand,
Mm.
those are two different compliance standards because
Right.
then you have to worry about near proximity, no proximity, or high powered far proximity to make sure that all those different scenarios are accounted for and they're within their own safety levels and safety distances.
Right. So, is it fair to say that simulation uh, doesn't necessarily replace compliance, but can significantly reduce the number of iterations and give you the confidence to pass the compliance the very first time when you go for it.
Yes, I would say definitely nothing replaces real world testing. That's the only way we'll
Yes.
finally know. But
Yes.
instead of real world testing 5, 6, 7 times, and in the world of compliance, that means maybe a year to 2 years.
Wow.
That is not something you want. Is an extremely slow process because it's
Mm.
very meticulous. So you want to diminish the number of revisions that you have to
Yes.
do for this product to make sure it passes, hopefully within the first time. And that is exactly why we simulate things. The most important thing in any design, it doesn't even matter with electromagnetics, in anything, is you need to know what to expect.
Right.
Having the ability to understand what to expect means that you're already a step ahead, which
Right.
means that when you throw it in the chamber in real life, you have a 90%
You're
certainty of what
almost
it's going to
certain.
look like. Yeah, you're almost certain. You're like, this, I know what it's supposed to look like. And if you see any variances, then you're like, all right, did I account for that in my simulation or is my setup in real life wrong? But now
Right.
that you have an expectation, you can work from there. You don't have questions of just why. You know
Mhm.
why. Now you can dig deeper.
Right. Yeah, yeah, makes absolute sense. In fact, now that we are on the subject of, these iterations and getting to the final stage, tell us a little bit about the EMC certification and what it really takes for a device to pass this.
Yes, there's a lot. One, there's where we worry about fundamental power. So,
Mhm.
at the radiated frequency of the device, what is it? What is its power level? And within
Mhm.
the certification level that you want to apply for, is it within FCC's limits?
Right.
So, at its fundamental, let's say they give you a limit of this high, you want to make sure that you're just below that limit at your highest power that your device can emit. No device functions at the highest power that it can run at, but these tests are run at their highest power to make sure that in any case, in normal day-to-day use, they're never going to pass these FCC limits. Second, we worry about harmonics, something I brought up before. Harmonics
Mhm.
are really important because if you have a device that runs at this frequency,
Mhm.
but its harmonic is another frequency from that matches another product, you can cause interference.
Mhm.
An example could be that let's say you have a phone that its harmonics are out of whack. It
Mhm.
could affect maybe other different carrier signals. T-Mobile, AT&T. It could affect devices in your home. Sometimes you can notice this if you have an older microwave and you turn it on, it'll mess with your Bluetooth headphones. You won't be able to hear really clearly or cut the signal. That's the idea of interference and worrying about fundamentals and harmonics when it comes to the outputs of these devices. Testing it in the anechoic chamber, which is what we see in this image here, gives us the exact view of what it's going to look like outside in the real world. And if it passes within the limits that FCC has set, or whatever country you're in with their limits, it's going to be intrinsically safe for its situation.
All right, understood. Now, if I may take a step back, help us understand what we're seeing here. And also, you mentioned that the power levels are measured. Are there some sort of sensors that are placed around the device at certain distances, or how is this testing done?
Yes. So what it's connected to is a spectrum analyzer. Spectrum analyzer will be connected to an antenna. We can see to the right of the screen
This
that
one, right?
yes, that's a periodic log antenna. That is what the spectrum analyzer is connected to. And
Mm-hmm.
these are very broadband antennas. So they can receive a huge range of frequencies.
Right.
I don't know the specifics of that antenna, but it could be up to 10 to 20 gigahertz range where they can take in these frequencies. So they can account not only for fundamentals, but for the harmonics up to the 10th harmonic of a device. And then
Right.
also the capabilities of the spectrum analyzer is a limiting factor within that as well. But how do you make sure that the device you're testing isn't in an environment where it's not accurate? Well, that's
Mm.
what all the cones you see are for.
Okay.
That shape is not by accident. That
Okay.
reduces any reflections within the room so that whatever your device is transmitting and whatever the antenna on the spectrum analyzer is receiving, there's nothing else happening. There is no bouncing around. And also, these rooms are completely sealed that where any outside electromagnetics do not come in. The only thing that that antenna is measuring is the device under test in front of it and nothing
Wow.
else.
So it must be a really quiet room then,
Extremely quiet. It's also like it's secondary thing because sound is just waves too, right?
right?
You get no echo in these rooms.
Yeah.
The quietest room in the world uses designs like this. Basically, that the quietest room in the world is also probably a great anechoic chamber for testing as well,
Wow.
because it just eliminates any sort of reflections or bouncing around when it
That
comes to these
experience
far field.
must that experience must feel like you're in space or something if it's that quiet.
It's fun. Yeah, it's awesome. And it's not just as simple as putting a device straight in front
Sure.
and measuring it and you're done. The device needs to be rotated 360, moved on an angle left and right. When devices radiate, they have far field radiation. They're not just perfect circles. We have low.
I lost your audio for a second, Mark. No, I cannot hear it. Let's check with the audience. Okay, running a quick check with our audience.
All right, I should be back on. Can everyone hear me?
Yes. Yeah. Yeah.
Sorry,
All
technical
right.
difficulties.
Okay. No problem.
Not everything wireless is very consistent. This is a wireless headset, and
Okay.
glitches happen. All right. What was the last thing you heard me say? Just so I can
So,
retrack.
I think we were talking about the experience inside the room being close to space.
Yes, no, it's a super surreal experience.
Right.
It's really technical. The distances between the antenna and the device under test are very accurate too. And when
Mm,
you're in there, you feel like you're part of, I don't know, a pretty big process. You're like, wow, like
nice.
this is what you saw in the movies as you were a kid, like the people in the lab testing all this stuff. You're like, why does it look so crazy? And then you, in real life, you're like, oh wow, there's physics and reasons behind why
Behind it,
we
right?
have these weird spiky rooms that we test in.
Nice.
So yes,
Yeah, that's a That's a really cool experience. In fact, I remember seeing something similar to these cones behind, people who do podcasts and YouTube videos in order to deaden the sound in their
Yes.
rooms, right? Yeah. So anyway, getting back to compliance, I guess in general, one out of every two products fail the testing requirements on time, and that clearly results in a lot of time and effort. And what you just mentioned is you cannot launch a product until the requirements are met, right?
Yes.
Do you have any examples or experiences that you could share?
Yes, so at least at Inovonics, we do pre-testing. So
Hmm.
whatever product we want to send out to get officially tested in, because you have to get these products tested in an official lab for
Hmm.
FCC to approve it.
Right.
We have anechoic chambers and all the tools we need in-house in our lab to make sure that when we perform pre-testing and it passes under our situation, when we send it out to the labs, we're going to see the same results. So it's extremely important to pre-test any device that you make within a lab, or if you can work with another lab, just to get a situation that's set up near what the official testing sites will look like, because you can fail 100 times inside and you're not going to waste time. But if you fail once when you're near the final end product of your design, it's going to maybe delay your product launch by 6 months
Mm,
minimum
mm.
because of the
Wow.
redesign process, the fact that you failed and you have to go back to the drawing board. Um, with simulation tools and with proactive testing, you can eliminate basically, like at least within Inovonics, we pass our tests officially every time. Once we're
Wow.
done with the simulation work, with the pre-testing, and we officially send our device out to the tester, we know it's going to pass. And we usually, almost every time, get a result back saying, hey, you've passed. Here's the test report. Good job. And
Wow.
it's less of a worry. We never worry if we send a device if it's going to pass.
Mm.
We do all that worrying, making sure it passes in-house, and we send it out. It's just a waiting game. We're waiting for a report, and we're good to go.
That's awesome. I mean, the confidence that combination of simulation and pre-testing is giving you, I think that that's great. And is it fair to say you probably do a lot more simulation and lot less pre-tests? Um,
Yes, I would say because of once you understand the testing environment you're in and you've simulated enough and created enough devices within your like your environment, basically most of the work is within the simulation. And when you
right.
get the device out to do pre-testing, it's either small tweaks to the design, so Rev 1 to Rev 2, or it looks exactly how you expected it. You're like, okay, this is great. We are within our limits. There are many antennas I've designed where literally first shot, Rev 1, it's passed all our tests, all our anechoic chamber tests, and it's hit the mark exactly of how I've wanted it to match and radiate. So and that takes time to dial in
Of
for
course.
your environment. Takes practice, takes work. But once you're dialed in within the environment that you work in, you can pump out new designs basically and have a really good percentage of confidence that it's going to be what you're expecting.
Right. Okay, yeah, very cool. In fact, you wanted to share a example of a game controller. Maybe in the interest of time, you can quickly provide a 30-second overview of what we are looking at.
Yeah, so this is kind of just a nice visual example of what I was talking about, working within limits and working without limits, or outside of the limits. So this is a game controller, and we have this E field and at the 1.29 gigahertz that it's functioning at, and we have ideal scenarios and unideal scenarios. With this simulated example, with the correct setup, our lines do not couple with each other, and when or they couple slightly. Nothing doesn't just ever couple, but you were coupling enough within that when we run our FCT tests and our limits, we're under the range. Now, if we're looking at the other example to the bottom of the screen, we see a more realistic view. Let's say it wasn't optimally designed, or we're testing out a Rev 1 of this controller, and we see that, all right, we're seeing a lot more coupling than we'd like, and we're actually passing the thresholds that we have that is set for compliance. So this gives us a great idea of kind of what the level of play you get with what's allowed with your design. Not, you can't make everything perfect, and not
Of
everything can
course.
just be completely isolated from each other.
Mhm.
But what's nice about the limits is you can understand how much play you get with um, these limits. And
Yeah.
this is what we can,
So it's
this
a
is what we're
very
showing on the
clear
screen.
example. Even for a mechanical engineer like me with no background of electromagnetics, I can see the difference, a slightest change in the design resulting in failure of, or change in assumption resulting in failure to pass compliance. That's, yeah, that's very
Yeah.
interesting. Okay, so let's switch gears, talk about the challenges that uh, you typically experience at Inovonics from a product design standpoint, from an antenna design standpoint, and how you go about it.
Yes. So we have three main challenges that at least I've categorized these three main challenges when it comes to the type of antennas that we build.
Right.
One is model for dielectric detuning. What is a dielectric? Dielectric is basically the electric status of a device. So how does it interact with the electromagnetic fields around it? And that's what sets up its dielectric number. Plastic is 3. Metal is in the thousands, or it's or not thousands. Sorry, metal is really really low. The
Mhm.
highest dielectric constant in the world is actually in the universe is water at
Oh,
80.
oh
Um,
wow.
so, and your hand is very near that dielectric constant. So it's a great way to kind of simulate what it means to if a hand comes into close proximity. But we worry about dielectric detuning because that is the main thing that interacts with the performance of our antennas in our devices. Um, and the example you see to your left, it's a metal box,
Right.
the PCB behind, the antenna, and then the plastic enclosure in front. Every single one of those different materials and their distances from each other affect the performance. And that is what dielectric detuning is. And then the second thing, which I lightly talked about, is antenna placement. The distance between that antenna and that PCB behind it, and its whole distance within the metal box and its proximity to the plastic enclosure in the front all have to be exact. If these are wrong, if you do not account for this, if you do not simulate for this, your device will not work as you expect at all. So these are extremely precise distances that you, through simulation, through trial and error, and through optimization, get to the right point to make sure that everything works accordingly. And then the last and most important thing, and the beauty of simulation, is seeing the unseen. In real life, we're not birds. We can't see electromagnetic waves. We don't know how these are working with our own eyes. But being able to get a good sense of what it should look like through simulation, you can understand if you've made any mistakes in your design. You can see hot points. You can see that, oh, I did not connect this correctly, or this is wrong. This is not matching up well. Being able to get that visual before ever seeing the product in real life is a really, really powerful tool.
All right. I think these challenges are very clear. Um, I guess the very first step is ensuring that there's tight integration between whichever simulation solution you're choosing with SolidWorks, right?
Yes.
So here is the example, or the elaboration of the example that you showed earlier, where we are able to launch the electromagnetics engineer role within the 3D Experience platform directly from the SolidWorks UI. Um, and I would imagine, you go back to SolidWorks, make a design change. It's very easy to update. The same
Yeah.
in the electromagnetics engineer role. So tell us, how important is this integration at Inovonics?
If we did not have this integration, we would have not come up with such a clever design as we have. Uh,
Okay.
me being able to really closely work with our mechanical engineers and have this back and forth between SolidWorks and CST, it allowed, I think, a perfect mesh between what it means to design something mechanically and design something electromagnetically. Uh, my coworker and I designed this plastic enclosure with the metal box to be exactly what we needed. There was
Mm.
no compromise because the design process started with both of us immediately. He did not design something and then I had to fit it in, or I did not design something and he had to account for it. The process started with both of us together. If
Mm.
something didn't work for him, I could adjust. If something that he did didn't work for me, he can adjust. And it basically came up together to create this product, which I think is amazing. When you have a mesh of different engineerings happen at the same time from the get-go, everything is built for each other, not built and then accounted for later. You can design something really sleek and you know its functionality is going to be good.
All right. I think that's very clear. It's the synergy of two different applications that are helping you guys meet your specific requirements. While I guess working on the same revision, I guess revision management becomes very easy.
Oh, it's incredible. You can go back, see the changes, and what's nice is these designs are parameterized on
Mm.
the SOLIDWORKS side and the electromagnetic sides, which
Mm.
means you have full control. And you have full control of the parameters, and both sides get full control too. It isn't just one or the other, which gives a lot more flexibility and freedom when it comes to working with SolidWorks Engineer on these designs.
All right. Very, very cool. Um, Tell us a little bit about the electromagnetics engineer role on the platform, and the CST technology, and why you chose to go with this.
I went with CST because I think not only is the functionality of a product really important, but I think the usability and the approachability is really important too. And I think CST has set it up in a way where if you are familiar with antenna design, electromagnetic design, everything you need is at your fingertips in a really accessible way, where it makes it look simple, but it's really powerful under the hood.
Mm.
So you're like, yeah, I click these couple buttons, I do exactly what I want. While in another program, it could be an entire process to get that same result. So CST is a great way of simplifying complex scenarios to make sure that the only thing you have to worry about is doing your design and you're not worried about fixing the software or moving around the software to accommodate to your needs. That's why I chose it. Also, CST has a huge uh, width of applications, not only from what I do, but when we expand and we have different scenarios we want to account for. As we can see on the screen, this is our wall mount locator that I've designed, and we're setting up in a room application to see optimal locations. In the future, we can get it so that we can get floor plans delivered, like sent to us, and we can build up these models, and I can see for an entire building how we need this set up, which saves maybe what, a week worth of setup time in the real world of where and how to put these antennas to make sure that they're optimally set up. There's a huge library of already pre-built antennas and pre-built systems to make sure that you can have good like reference designators. You can have a good starting point with something. Um, that's awesome. And then also not only with electromagnetic design, but we can worry about thermals. We can worry about signal and power integrity within a
Mm.
design. We can grab like the most commonly used application for ECAD PCB design is Altium. And Altium and
Okay.
SolidWorks have a direct link with each other, which means that
Mm.
SolidWorks users can grab the entire layer stackup and design entire PCB design from Altium. And now that we can perfectly share between SolidWorks and CST, that means I get the exact design too. So I can run these
Nice.
signal and power integrity analysis. I can run these thermal analysis within CST and basically get all the results we need before we ever even make the product.
Very cool. So just to summarize, it's the combination of comprehensive capabilities offered by the CST solver technology, user experience, ease of use, catering to large set of applications, and then integration of both mechanical CAD and electrical CAD to perform these complex simulations. I
Yes,
think
which is
I think
probably the
it's
most
these.
important feature is that integration
Right,
because it
right.
saves so much time not worrying about how to send files,
Mm.
making sure the revs are up to date. Oh, did you send me an old one or did you send me a new one?
Mm.
Um, I've dealt with that in the past. It is a nightmare.
Nobody
Um,
likes to deal with this.
yes, it's great to avoid it. And one
Yeah.
last note, also, it's really important that CST has compliance built in.
Mm.
You do not see that a lot, at least at the level of simplicity that it shows it in CST. It'll show you, hey, you want to do SAR compliance
Mm,
simulation?
mm.
Here's a button for that. Go set it up. That is great. That is a
So
really, really,
you could overlay the performance of the device on top of the compliance limits, just like what you were showing in the game controller example earlier, and see
yes,
if it meets the requirements or not. Yeah, that's very
exactly.
cool.
So now you get that all set up and you haven't even made it yet, which means you've saved a lot of time.
Okay, yeah, I think it's clear. Now let's take a look at how you've been addressing the three challenges that you talked about earlier using the electromagnetics engineer role on the platform.
Yes, let's dive deeper into that.
So, in the interest of time, we can probably start off with your typical antenna design process and constraints very quickly. So, I just want to warn you that there's 10 minutes left, but we can go over by about 4 to 5 minutes. So, maybe
Okay.
for the benefit of our audience who are primarily from mechanical design background, can you quickly explain the antenna design process and constraints, and then we go into those challenges?
Yes. So with any design, you need to first do research. Having a really powerful simulation tool is not enough. You still need to understand the physics of what you're designing, and you need a baseline. You need a baseline design to start with. So that's research papers, searching online, past experience. You use all that to build your new and upcoming design. After you've done all your initial calculations and all your kind of tissue paper math, you can build a very basic design in CST and see its initial performance. Now, this is where the beauty of CST comes into place with the optimization, parameterization, and model building that you can perform to get to the point where you want it to work well. Then you integrate it with SOLIDWORKS to get your enclosure in-house to make sure that everything works well with the enclosure that we've designed together in the field. We test it. We compliance test it. We make sure those pass within all the stuff that we've already counted for in simulation. And then if we have to do another rev, we take the results we measured in the lab, cross compare it with the first results received in simulation. We can tune the materials and tune the environment to closely match to the real world setting that we tested in, which will basically guarantee your next design coming out through whatever you simulated will look very near to real life. And then you can ship a product from there.
All right, very interesting. I think it's clear what the high level definition of an antenna design process is. Let's start with the three challenges, right? So you talked about model dielectric detuning. Um, Help us understand how you decide the proximity of different materials.
Yes. So the proximity is the most important thing. In this case, I was designing an antenna that was supposed to work inside a metal box,
Mm,
which also not a great start, right? You don't want an antenna in metal, right?
right.
But this is an application that had to happen, and one we personally haven't seen done in the industry before. So we had to get creative. One was making sure that one was the idea that we're going to split the antenna away from the motherboard and use the
Mm,
motherboard as a backplane for this antenna. So anything that reflects into it will reflect off the PCB instead of reflect off the metal box, because if we reflect off the metal box, we're going to create box modes within it, and that will cause all mayhem to our performance. And that's the importance of dielectric detuning, because to account for the motherboard and its material and the box and its material and the plastic cover in front, if you do not have the materials set up appropriately, you are not going to get a good idea of how this antenna is going to work in real life. This is, I think, the most important thing to account for initially is the dielectric detuning of
okay.
whatever's around your antenna.
Yeah, and also I guess what you're showing here is on the left hand side, you've got the antenna performance in a standalone environment,
Yeah.
and on the right hand side is the integrated environment. I see different colors for this
Yes.
electric field plot. Do explain that to a emag ignorant like myself.
Yeah, so I like to call this the eye candy of the software, but it gives us a good idea of how. Not only do we see EMAG, we can see H fields as well. We can see surface current. We can visualize all this within the software, and this gives us a great idea of how this is interacting with its environment around it. If we see a lot of hotspots, red points at
Mm,
corners and peaks, we know that, all right,
okay.
yeah, and that's it just working by itself. And by alone, this antenna is meant to work in its box. It's not
Mm,
meant to be by itself.
right.
So the results we're seeing is that standalone antenna, where it's meant to be in the box, is completely shifted because it is alone. But we're seeing it in
Ah,
the enclosure, how everything's affecting it. We see everything in the blues or the greens, which means
oh
we're not
wow.
seeing crazy coupling. We're not seeing a lot of interference where we do not want it.
Okay, wow. That's kind of counterintuitive. That it's actually designed to perform inside an enclosure so that when you look at it in a
Yes,
standalone mode, it doesn't perform up to the standards. Wow.
it's crazy, but yeah, we're the fact that we have the ability to do this is insane. That you
Yeah.
can design an antenna to only work in its specific
Environment.
enclosure, and instead of just hoping it does when you make it standalone and throw it into something.
Nice. Very cool. Tell us about the antenna placement, finding the right
Yes.
location.
So specifically with this product, this is a locator product. This is for a senior home, so people will be wearing pendants or holding stuff in their hand, and
Mm.
it's really important that we get the tracking right, the room positioning and location right. If someone falls, we need to know that the antenna detected that, and it leads back to the nurse the exact room that they fell in. We cannot have
Oh,
cross room interference where they fell in room 301, but they're actually in 302. That's a
okay.
huge deal. So performing simulations like this is not only important and not only save times, it's also life-saving at the end of it. If we can
Wow.
guarantee that the placement of our antennas make sure that our room accuracy is within the standard, we can be confident that when we place these in real life and run our own testing, we're not only saving time, but now we have the confidence that if someone falls, we know where they are and we can get to them in time. And that's what we're showing in these setups. We're showing the antenna in different corners of the room. We're showing the benefit of maybe having two locators in one room if we're having a divider in between. Every room is different, every setup is different. We can even simulate if we have it mounted in the ceiling and see its
Mm.
effects down on the room in the ceiling. Um, and then implementing actual floor plans means that you can actually account for any customer specific scenario when it comes to installing these systems.
Wow. I mean, simulation saving lives. That's amazing. So just so I understand it right, you've got the senior folks wearing the pendant that is communicating with some sort of a console or a unit, and you're trying to find out the best location to place the unit so you get the right information
Yes.
on the
So
location, right?
not only does the wall mount locator communicate with the pendant, but it
Mm.
also communicates with the unit that
Ah,
talks to why this design is so unique, which I should have touched on before, is that
sure.
it's a dual band antenna. It works at two
Okay.
different frequencies, but on
Okay.
one antenna. And that all works within the metal box, implanted into a drywall, where if anyone looks at it, it just looks like an outlet. No one could ever expect that there's this much tech and this much physics behind the wall. But yeah, not only do we get location within the room, tracking with the pendant, but it also directly communicates with our gateway to then talk to our nurses through the cloud to make sure that everything comes on time and we are accurate to where we need to be.
That's really cool. Okay, I think we are reaching the edge of the hour. Maybe you can quickly touch upon the third challenge and how you went around designing what fits within the packaging constraint.
Yes. So luckily we've touched on this a bunch already, so I don't need to dive too deep into this, but
Mm,
having everything packaged within this metal box and also making sure it works is extremely important because you have the antenna and the PCB too deep into the box, it's not going to work. You have it too outside of the box, it's not going to look as sleek and as flush as our design constraints allow because
mm,
the whole purpose of this product is to be inconspicuous. No one's supposed to
mm.
know that it's set up, and this is for safety reasons, so people do not mess with the locators.
Right.
So it's extremely important to not only get a good understanding of how we can package this design together, but also make sure it still functions correctly within our packaging constraints, and that we can actually visualize and see that performance after we're done setting it up.
Okay. Very nice. All right. So maybe you can wrap this up with some of the benefits Inovonics has realized by leveraging this unified modeling and simulation approach between SolidWorks and 3D Experience platform, especially for design of wireless systems.
Yes, of course. So we have realized not only a huge impact in our revision time, we're going
Hmm.
from 4 to 5 revisions on the RF side to 1 to 2, which is months of time saved,
Hmm.
which is incredible. I have the ability to work on almost any device because of the cloud infrastructure. So I can work off my iPad, off my laptop, off my PC, almost anywhere in the world. I just need a good internet connection, and I don't have to worry about any power or any like horsepower to run these simulations because I can use the online cores and online features that we have to run anything I need. We have perfect dock control. I understand all my revisions. Everything's saved online. I can grab them off of one device and throw them on another without any concern. And all of this is to just accelerate design and make sure that the only thing you have to worry about is being an engineer and not worrying about the softwares that you're using.
That's a very important point. Focus on engineering versus picks and clicks, right?
Yes,
One topic we didn't get to touch upon is the high performance cloud computing. I imagine that electromagnetic simulations are pretty compute intensive and can result in
extremely.
exorbitant hardware and software costs from an IT perspective. I would think that this is a big value offered by 3D Experience platform, especially for electromagnetic simulations.
Huge. It's no comparison. You usually need a gigantic server that you need to log into. That's usually
Mm.
shared resources with other engineers in your company.
Right.
This way, you can get dedicated cores run for your specific product, and
Hmm.
you can choose as many cores and GPUs as you require to get the result you need at the time that you need it.
All right. Yeah, makes sense. And I would also imagine that your turnaround time would have increased, would have reduced drastically. What used to take you probably days, if not weeks, might probably be taking you hours, if not days, to
Exactly.
get a quick feedback and then make the right design change.
It's incredibly the difference is huge.
Okay. Okay, I think those are some of the key points we wanted to discuss. I do want to bring up to our audience that Mark was actually on the stage of 3D Experience World 2024 in Dallas this year. There's a link right here for the YouTube video that has the recording of Mark's presentation at 3D Experience World. I mean, he did a fantastic job. As you could see, he's a naturally talented speaker along with being a naturally talented engineer. So do check out his session at 3D Experience World. Mark, thank you so much for your valuable time. I know we are out by a couple of minutes. Maybe we can take a couple of questions if you're okay to stay a bit longer.
100%.
Okay, there was one question. I think you kind of touched upon it from Vamshi Krishna. The question is, which type of materials are typically used in enclosure design, and which one is the best and why? I think it's like three questions.
Yes. And that the best answer for that is it depends. One, there is a wrong answer, which is using any conducting materials. So you don't want metal or a Faraday cage or surrounding your antenna, you will diminish performance. If you put your Wi-Fi router in a metal box, suddenly nothing gets Wi-Fi in your house anymore, and there's a reason why. The best materials I have found so far is honestly just ABS plastic or just different materials of plastic, nylon, depending on your device, it could be wearables, cloth. But on any device you see, even if it's made out of metal or glass, the antennas are covered in plastic. They're not covered in anything else. Even on your iPhone or your Samsung or any devices, look closely on the bands, touch them with your finger. They are not metal, they're plastic.
Mhm. All right, thanks for that, Mark. I think there was another hand raised by Miguel Corona. Let's see if he has any question. We'll give it like 10 seconds. Um, if not, I guess we can go ahead and wrap up. Well, again, thanks to all the audience who've taken their valuable time to join us, and huge shout out to Mark for being here, sharing his amazing insights and background, and giving us this quick crash course on electromagnetics, antennas, and the importance of designing compliant ready antennas. Thanks again, Mark. And I would also like to thank the crew behind this series who've done tireless amount of work in the background. Jill DePont, Ramesh Lakshmipati, Ronit, my co-host whom I missed today, and Eva Parchak from the Deso team. Thanks to all of you. With that, we're going to wrap up today's session. Thanks, everyone. And for those who may have missed, if your colleagues have missed the session, they can watch the recording, which will be published in a couple of weeks. The next session is going to be from PES, Practical Engineering Solution, where Tyler Cook, our good friend, is going to come in and talk about how simulation can actually ramp up consulting business and help you transform. That's it. Thank you, everyone, and have a good rest of your day. Thanks again,
Thank you
Mark.
so much for having me. Thank you.
All right. Bye.